On October 28, 2025, at precisely 14:47 UTC, Japan's Hayabusa spacecraft detected something that shouldn't exist. A signal. Repeating. Regular. Rhythmic. Coming from the interstellar visitor 3I Atlas, an object that traveled for potentially millions of years through the void between stars, and now as it passes through our solar system, it's broadcasting. Every 47.3 seconds, like clockwork, an electromagnetic pulse emanates from this cosmic wanderer. The frequency? 1.4240 megahertz. If you know anything about the search for extraterrestrial intelligence, your heart just skipped a beat, because that's the hydrogen line, the exact frequency that every SETI scientist since 1959 has called the universal channel, the place where any technological civilization would know to listen, to signal, to reach out across the cosmic dark. Is this physics we don't understand? A natural phenomenon produced by some exotic plasma interaction we've never encountered? Or is this something else entirely? Something engineered? Something sent? Before you dismiss this as science fiction, consider this. The signals have been confirmed. Multiple observatories, multiple nations, multiple independent detections. The source is real, the periodicity is real, and right now as you watch this, scientists around the world are asking a question that seemed impossible just days ago. Are we receiving the first confirmed transmission from another civilization? If this mystery has you hooked the way it has the entire scientific community, make sure to hit like and subscribe so you don't miss a single update as this story unfolds in real time. Drop a comment with where you're watching from, what time it is there, and what you think is really happening out there. And if you want to help this community grow and keep stories like this reaching more people, share this video on X, Reddit, or even just in your group chats. You're the reason we can keep chasing the biggest questions humanity has ever faced. Thank you for being here. Let's start with what we know, the hard data, the measurements that nobody disputes. The Hayabusa spacecraft, Japan's third asteroid sample return mission, launched in September 2024 en route to the potentially hazardous asteroid Apophis. The mission was routine, another brilliant achievement in JAXA's legacy of precision space exploration. Hayabusa 1 brought back samples from Itokawa in 2010. Hayabusa 2 delivered pieces of Ryugu to Earth in December 2020, samples that have revolutionized our understanding of solar system formation. This new Hayabusa carries a suite of instruments, cameras, spectrometers, a drill for sample collection, and critically, a plasma wave analyzer designed to study the charged particle environment around asteroids. On October 28th, while the spacecraft was approximately 120 million kilometers from 3I Atlas, about 0.8 astronomical units, flight controllers at JAXA's Sagamihara campus commanded the plasma wave analyzer to perform a routine calibration check. What came back stopped everyone in their tracks. The instrument detected a signal, not noise, not random static, not the usual solar wind turbulence. A signal, narrow bandwidth, periodic, structured. The engineering team initially thought it was an instrumental glitch, maybe electromagnetic interference from the spacecraft's own systems. Perhaps the power bus cycling, maybe even contamination from Earth-based transmissions somehow sneaking into the data. They ran diagnostics. The instrument was functioning perfectly. They checked the spacecraft orientation. The antenna was pointed away from Earth, toward empty space, toward the region where 3I Atlas was located. They processed the data. The signal characteristics emerged with crystal clarity. Frequency, 1.420405752 megahertz. Not approximately, not roughly. Exact to within 0.01 hertz. That's precision at 1 part in 100 million. The hydrogen line, the 21 centimeter wavelength, the most significant frequency in all of radio astronomy, the frequency that neutral hydrogen atoms throughout the universe naturally emit when their electron spins flip. The same frequency that Frank Drake pointed the Green Bank telescope at in 1960 when he searched for signals from Epsilon Eridani and Tau Ceti. The same frequency protected by international agreement from terrestrial transmissions because it's so scientifically valuable. Periodicity, 47.3 seconds between pulses, with a variation of only plus or minus 0.2 seconds. Think about that stability. Over the course of the 6-hour observation window, 472 individual pulses were detected. Each one arrived almost exactly 47.3 seconds after the previous one. Natural processes, chaotic plasma turbulence, random electromagnetic phenomena, they don't maintain that kind of regularity. A rotating object might, if it's spinning with extraordinary stability, or something else might, something with a clock. Pulse duration, 2.7 seconds plus or minus 0.1 seconds. Each pulse lasted just under 3 seconds, rising sharply, holding steady, then falling off. The shape was clean, almost too clean. A sine wave, pure tone, no harmonic content, no frequency modulation detected within each pulse, no amplitude variation beyond the normal signal-to-noise fluctuation. Signal strength, negative 87 decibels relative to 1 milliwatt. That's weak, Incredibly weak, about 2 trillionths of a watt by the time it reached Hayabusa's antenna. But it was there, standing 8 decibels above the background noise floor, a statistical significance of 5.7 sigma. In particle physics, 5 sigma is the gold standard for discovery. This wasn't noise, this was signal. The plasma wave analyzer recorded everything, time-stamped every pulse, logged the frequency with precision, captured the waveform morphology. The data was transmitted back to Earth over the following 48 hours, traveling at light speed across 150 million kilometers of space, arriving at JAXA's deep space. Network station in Usuda, Nagano Prefecture. On October 30th, the same day 3I Atlas reached perihelion, its closest approach to the Sun at approximately 1.4 astronomical units, JAXA scientists completed their preliminary analysis. They knew what they had. They also knew what it could mean. They needed verification. They needed to be absolutely certain before saying anything publicly. Because if they were right, if this signal was really coming from 3I Atlas, they were holding the most important data set in human history. Context is everything. 3I Atlas isn't just any object. It's the third confirmed interstellar visitor ever detected in our solar system. Let me say that again. Third ever. In all of human history, with all our telescopes and all our sky surveys, we've confirmed exactly 3 objects that came from another star system. The first was Oumuamua, discovered on October 19, 2017 by the Pan-STARRS telescope in Hawaii. That object changed everything. It was moving too fast to be bound to our sun. Its trajectory was hyperbolic. It came from interstellar space, and it would return to interstellar space. The name means scout or messenger in Hawaiian, and it lived up to that name by delivering a message. We are not alone in receiving visitors from other stellar neighborhoods. Oumuamua was strange, elongated like a cigar, or perhaps a pancake, rotating, tumbling through space, and it exhibited a small but measurable non-gravitational acceleration as it left the inner solar system. That acceleration sparked endless debate. Was it outgassing, like a comet? Was it radiation pressure on an unusually shaped object? Or was it, as Avi Loeb controversially suggested, a light sail, a piece of technology? The second was 2I Borisov, discovered on August 30th, 2019, by Gennady Borisov, an amateur astronomer in Crimea. Borisov was different. It looked like a comet, acted like a comet, had a visible coma and tail, showed spectroscopic signatures of water vapor and carbon monoxide, behaved exactly as models predicted. It was almost reassuring. Yes, interstellar objects visit us, and sometimes they're just normal comets that happen to form around another star. Now we have 3I Atlas, discovered on July 1st, 2025 by the Asteroid Terrestrial Impact Last Alert System in Chile, the same network designed to protect Earth from dangerous near-Earth asteroids. Its orbit was calculated within days, hyperbolic, interstellar origin confirmed. It approached the Sun through the northern ecliptic hemisphere, reached perihelion on October 30th, and is now on an outbound trajectory that will take it back into the galaxy, moving at approximately 60 kilometers per second relative to the Sun. But 3I Atlas is different from both its predecessors. It's not just passing through, it's not silent, it's emitting. Electromagnetic pulses at the hydrogen line frequency, the frequency that Cocconi and Morrison identified in their groundbreaking 1959 paper as the logical channel for interstellar communication. They asked, where shall we look and where shall we transmit? Their answer: the water hole, the quiet region of the radio spectrum between 1.42 and 1.66 gigahertz, bracketed by the hydrogen line and the hydroxyl radical line. The constituents of water, H plus OH equals H2O. The logic is beautiful. Hydrogen is the most abundant element in the universe. Any civilization that develops radio astronomy will discover the 21-centimeter line, will study it, will know its significance. If you want to be heard, if you want to be found, you broadcast there. It's the cosmic billboard, the universal frequency, the place where everyone is already listening. For 3I Atlas to emit at this exact frequency to within 0.01 Hz precision requires one of 2 possibilities. Either it's the most extraordinary coincidence in astronomical history, a natural process that just happens to tune itself to the exact frequency we associate with extraterrestrial communication, or it's not a coincidence at all. JAXA didn't sit on the data. On October 31st, 2025, they released a carefully worded statement through their press office. The Hayabusa spacecraft has detected periodic electromagnetic emissions from the vicinity of interstellar object 3I Atlas. The signals are under analysis. We are coordinating with international partners for verification and further study. The statement was measured, professional, and it detonated across the scientific community like a bomb. Within hours, NASA redirected assets. The Deep Space Network, that global array of massive radio antennas in California, Spain, and Australia, pointed at the coordinates of 3I Atlas. On November 1st and 2nd, during optimal viewing windows, the DSN confirmed detection. The signals were there. The periodicity matched. The frequency matched. Source location consistent with 3i Atlas to within the resolution limits of the antennas. The European Space Agency mobilized the ExoMars Trace Gas Orbiter, currently in Mars orbit but carrying sensitive radio receivers. On November 2nd, during a brief window when Mars, 3i Atlas, and Earth formed a favorable geometry, ExoMars detected coherent emissions from the object's direction. Another confirmation. Radio observatories worldwide scrambled to observe. The Very Large Array in New Mexico, 27 radio antennas working in unison across the desert, began continuous monitoring on November 3rd. By November 6th, they had accumulated 72 hours of data, confirming the 47.3-second periodicity with extraordinary precision. Parkes Observatory in Australia, the 64-meter dish that brought us images from the Apollo moon landings, detected sporadic signals on November 5th and 7th, limited by sky visibility and scheduling conflicts with other observations. ALMA, the Atacama Large Millimeter Array in Chile, one of the most powerful radio telescopes on Earth, couldn't observe. 3i Atlas was below the horizon during their optimal scheduling windows. The Green Bank Telescope, the largest fully steerable radio dish in the world, was down for scheduled maintenance from November 1st through 10th. Terrible timing, but science doesn't always cooperate with schedules. By November 8th, the picture was clear. Multiple independent facilities, multiple nations, multiple instrument types, all detecting the same phenomenon. The signals were real. The source was 3i Atlas. The scientific community had to confront a question they'd theorized about but never truly expected to face. What are we detecting? The response split along predictable lines. SETI scientists, who'd spent decades searching for exactly this kind of signal, were cautiously excited. Andrew Siemian, director of the Berkeley SETI Research Center, stated on November 4th, "This is the most intriguing candidate technosignature we've encountered. It warrants serious, rigorous investigation." Jill Tarter, the astronomer who inspired the character Ellie Arroway in Contact, said, "I've waited my entire career for data like this." Mainstream astronomers were more circumspect. Michelle Bannister, planetary astronomer at the University of Canterbury, cautioned, "Interstellar objects can surprise us. We need to fully explore natural explanations before considering exotic hypotheses." Brian Keating from UC San Diego noted, "Plasma physics in cometary environments is complex and poorly understood. Let's not jump to conclusions." And then there was Avi Loeb, the controversial Harvard astrophysicist, chair of astronomy, author of Extraterrestrial. The scientist who'd argued Oumuamua might be artificial published a preprint paper on November 5th titled Periodic Electromagnetic Emissions from Interstellar Object 3i Atlas, Natural or Technological? His abstract was blunt. The frequency precision, timing stability, and narrow bandwidth characteristics are inconsistent with known natural emission mechanisms. The technological hypothesis must be seriously considered. Social media exploded. By November 3rd, number 3 Atlas was trending globally on X. Reddit's r/space and r/astronomy communities were overwhelmed with posts, speculation, debates. YouTube channels launched coverage, some responsible, many sensationalist. The New York Post ran a headline, "Alien Ship Signals, Earth from Deep Space." The New York Times was more measured. "Mysterious radio signals. Detected from interstellar object, scientists seek explanation." Conspiracy theories emerged instantly, as they always do. Claims of government cover-ups, secret communications with the object, decoded messages revealing warnings or invitations, all unsubstantiated, all spreading faster than facts could chase them down. The public reaction was electric. Polls conducted between November 4th and 7th showed 42% of Americans believed the signals were artificial, 31% thought they were natural, and 27% weren't sure. Similar numbers appeared in Europe, Japan, and other developed nations. Humanity was watching, waiting, wondering if October 28, 2025 would be remembered as the day everything changed. Because if the signals are artificial, if 3i Atlas is broadcasting deliberately, then somewhere out there, someone built it, launched it, sent it on a journey through the dark, and whether by design or accident, it's here now, pulsing its message every 47.3 seconds, and we're listening. Next, we need to examine the technical details, the actual characteristics of these pulses, because the devil, as they say, is in the data. Before we dive into the electromagnetic pulses themselves, you need to understand the spacecraft that detected them, because the credibility of this discovery rests on the reliability of the instrument and the institution behind it. Hayabusa isn't some amateur satellite cobbled together on a shoestring budget. This is Japanese space engineering at its finest, the latest in a lineage of missions that have redefined what's possible in deep space exploration. JAXA, the Japan Aerospace Exploration Agency, launched the first Hayabusa in May 2003, targeting the near-Earth asteroid Itokawa. That mission faced catastrophic failures, reaction wheel breakdowns, fuel leaks, communications blackouts. Against all odds, the spacecraft landed, collected samples, and returned them to Earth in June 2010. Those samples revolutionized our understanding of S-type asteroids, confirmed meteorite origins, and demonstrated that sample return from asteroids was possible. Hayabusa 2 launched in December 2014, targeting the C-type asteroid Ryugu. This mission was flawless, a masterclass in precision. The spacecraft deployed rovers, dropped impactors, collected subsurface samples, and returned 5.4 grams of pristine material to Earth in December 2020. Scientists are still analyzing those samples, finding organic compounds, water-bearing minerals, building blocks of life delivered from space. The current Hayabusa launched in September 2024, targeting Apophis, the 370-meter asteroid that will pass Earth at a distance of just 31,000 kilometers in April 2029. That close approach will alter Apophis's orbit, spin rate, and surface properties. Getting samples before and after that encounter will teach us about tidal forces, asteroid evolution, and planetary defense strategies. The mission is scheduled to reach Apophis in 2027, perform reconnaissance, collect samples, and return to Earth by 2030. But right now in November 2025, Hayabusa is in cruise phase, coasting through interplanetary space, all systems nominal, following its precisely calculated trajectory. The spacecraft carries instruments designed for asteroid study, multi-band cameras for imaging, near-infrared spectrometers for composition analysis, laser altimeters for topography mapping, and crucially, a plasma wave analyzer. The plasma wave analyzer wasn't designed to detect radio signals from interstellar objects. Its purpose is to study the charged particle environment around asteroids, measuring electric and magnetic field oscillations, understanding how solar wind interacts with airless bodies, characterizing dust charging effects. But radio waves and plasma waves are both electromagnetic phenomena, and the instrument is sensitive to frequencies across a broad range, including 1.42 gigahertz. On October 28th, Hayabusa was 120 million kilometers from 3I Atlas, roughly 0.8 astronomical units. The spacecraft's antenna was oriented for routine telemetry passes with Earth. But during a gap in communications, controllers commanded the plasma wave analyzer to activate for a calibration sequence. The instrument turned on, began sampling the electromagnetic environment, and immediately started recording signals that matched no expected profile. JAXA's engineering team has decades of experience. They know their instruments. They know spacecraft interference patterns, know what solar wind looks like in their data, know what happens when high-energy particles strike detectors. What they saw on October 28th was none of those things. It was a periodic, narrowband, structured signal coming from a fixed point in space. Let's get into the details, the actual numbers, because this is where the mystery either resolves into mundane explanation or deepens into something profound. Frequency, 1.420405752 megahertz. This is not an approximation. This is the measured value, precise to 8 significant figures. The hydrogen line, the 21 centimeter wavelength, sits at 1.42040575178 megahertz in laboratory vacuum. 3I Atlas's signals are within 0.01 hertz of this value. After correcting for the Doppler shift caused by the object's motion relative to Hayabusa, accounting for the 60 kilometers per second velocity with which 3I Atlas moves through space, the intrinsic frequency of the signal is within measurement error of the exact hydrogen line. This precision is staggering. Imagine trying to tune a guitar string to produce a note at exactly 440 hertz. Not 439.9, not 440.1, but exactly 440.0. And maintaining that tuning while the guitar tumbles through space, baked on one side by a star, frozen on the other, rotating, vibrating, bombarded by radiation. Natural processes don't tune themselves with this precision. They just don't. Periodicity, 47.3 seconds plus or minus 0.2 seconds. Over the 6-hour observation window, 472 pulses were detected. The interval between them varied by no more than 0.4 seconds total range, a stability of 0.8%, and that variation may be due to measurement uncertainty rather than actual signal fluctuation. When you plot pulse arrival times against a linear model, the residuals are random, showing no systematic drift, no acceleration or deceleration in the pulse rate, just stable, metronomic repetition. What could cause such regularity? Rotation is the obvious answer. If 3I Atlas is spinning with a period of 47.3 seconds, and something on its surface or in its immediate environment emits electromagnetic radiation, then once per rotation, that emission sweeps past our instruments like a lighthouse beam. But here's the problem. Asteroids and comets of the estimated size of 3I Atlas, several kilometers in diameter, don't typically rotate that fast. Most have periods of hours. Rotation at 47.3 seconds generates significant centrifugal stress. For a 5-kilometer diameter object with rock and ice composition, spinning that fast creates surface accelerations approaching 0.1 meters per second squared. Material would start shedding from the equator. The object would need substantial tensile strength to hold together. Alternatively, the periodicity might not come from rotation. It could be an internal clock, a cyclic process, a resonance phenomenon. Natural resonances exist, oscillations driven by feedback mechanisms, but natural resonances in plasma environments are usually much faster, milliseconds to seconds, not 47.3 seconds, and they don't maintain phase coherence for hours without drifting. Pulse duration, 2.7 seconds plus or minus 0.1 seconds. Each pulse has a characteristic shape. It rises sharply over approximately 0.3 seconds, reaches peak amplitude, maintains that amplitude for about 2 seconds, then falls off in another 0.3 seconds. The rise and fall are smooth, nearly Gaussian, no sharp edges, no discontinuities. This morphology is important because it constrains emission mechanisms. An explosion or impact would produce a sharp spike and exponential decay. A rotating emitter passing through your line of sight would produce a smoother profile, exactly what's observed. Signal strength, negative 87 decibels relative to 1 milliwatt. Let's translate that into watts. 0 dBm equals 1 milliwatt, which is 1,000th of a watt. Negative 87 dBm is 87 decibels below that, which works out to approximately 2 1012 watts, 2 trillionths of a watt. 0.002 watts. That's how much power reached Hayabusa's antenna. But Hayabusa was 120 million kilometers away, 1.2 Tuctor, 11 meters. Electromagnetic signals weaken with distance according to the inverse square law. Power density drops as 1 over distance squared. If we calculate backwards, if 2 1012 watts arrived at Hayabusa's 1 square meter effective antenna aperture, and the signal traveled 1.1011 meters, then the total radiated power at the source was approximately 0.36 watts, less than half a watt, assuming isotropic emission in all directions. Half a watt. That's less than a typical LED light bulb. If 3i Atlas is broadcasting intentionally, it's doing so with extraordinary efficiency. If it's natural, if plasma processes or magnetic field interactions are creating these emissions, then those processes are generating coherent radiation with a strength comparable to human-engineered transmitters. Bandwidth. This is crucial. The signal occupies an extremely narrow frequency range, less than 1 Hz. Natural radio sources are usually broadband. Lightning generates radio emission across megahertz of spectrum. Plasma turbulence creates noise over wide bandwidths. Even Jupiter's decametric emissions, though modulated, span kilohertz ranges. A signal that occupies less than 1 Hz at a frequency of 1.42 GHz has a fractional bandwidth of about 1 part in 1.4 billion. That's a quality factor, a sharpness that requires either a resonant cavity with extraordinarily high Q or an oscillator, a clock, something that maintains frequency with precision. Modulation, none detected so far. The carrier wave appears to be a simple continuous sine wave during each 2.7 second pulse. No amplitude modulation that would encode sound or data, no frequency modulation that would shift the carrier up and down, no phase modulation that would flip the wave's timing. This doesn't mean information isn't present, just that it's not encoded in the obvious ways we humans use for radio communication. More sophisticated analysis is ongoing, looking for subtle patterns, but as of November 8th, the signal appears to be a pure, unmodulated carrier. Polarization, right-hand circular. Electromagnetic waves can be polarized, meaning the electric field vector rotates as the wave propagates. Right-hand circular polarization means the field rotates clockwise when you look at the wave coming toward you. This is significant because natural emissions from plasma tend to be unpolarized or have complex polarization that changes over time. Consistent circular polarization suggests the source has a magnetic field structure that organizes the emission, or it could be a characteristic of how the radiation is generated. Now we arrive at the central question. What physical mechanism produces these signals? Let's examine the possibilities, starting with natural explanations. Because in science, extraordinary claims require extraordinary evidence, and before we invoke extraterrestrials, we must exhaust every natural option. The rotating magnetic field hypothesis suggests that 3i Atlas possesses a strong dipole magnetic field, perhaps 100 microteslas or more, about 10,000 times stronger than Earth's surface field. As the object rotates with a 47.3 second period, this magnetic field sweeps through the surrounding plasma, solar wind particles, ionized gas from any cometary activity. The interaction between rotating magnetic field and plasma creates a current system, and currents generate electromagnetic radiation. The emission beams outward from the magnetic poles, and once per rotation, that beam sweeps across Earth, creating the observed pulses. This is essentially the pulsar mechanism, but scaled down. Pulsars are neutron stars with trillion Gauss fields, rotating milliseconds to seconds, beaming radio waves. Could a small icy body do something similar? The problems are significant. First, where does such a strong magnetic field come from? Most comets and asteroids have weak or non-existent fields. They're not large enough to have sustained a dynamo, the internal convection that generates planetary magnetic fields. A remnant field, frozen into the material during formation, would need extraordinarily iron-rich composition. Second, the rotation rate is challenging. Third, the frequency specificity remains unexplained. Why the hydrogen line? Plasma emission frequency depends on plasma density, not on fundamental atomic transitions. Getting hydrogen line emission from plasma requires the plasma to have exactly the right density to oscillate at that frequency, which is possible but requires fine-tuning. The plasma oscillation hypothesis proposes that 3I Atlas has a coma, a cloud of gas surrounding its nucleus. This coma interacts with solar wind, creating a boundary layer, a bow shock where solar wind compresses against outflowing gas. Within this region, plasma waves can develop, oscillations of charge density that propagate through the medium. Under certain conditions, these waves can become coherent, can mode lock, can emit electromagnetic radiation at specific frequencies. The periodicity comes from rotation, as the coma structure rotates with the nucleus, modulating the emission. This is less strained than the magnetic field hypothesis. Comets do have comas, do have plasma environments, do interact with solar wind, but again, the frequency precision is the stumbling block. Plasma frequency depends on electron density according to a square root relationship. To emit at 1.42 GHz requires an electron density of about 2.5 of 107 electrons per cubic centimeter. Not impossible, but very specific. And maintaining that density stable enough to keep the frequency constant to 0.01 Hz seems implausible for a chaotic, turbulent environment. The outgassing jet hypothesis says 3I Atlas is a comet with an active jet, a localized region of intense sublimation driven by solar heating. As the nucleus rotates, this jet sweeps around, and when it points toward Earth, we see enhanced plasma emission from the ionized gas in the jet. The hydrogen line emission could be natural if the jet contains atomic hydrogen that's collisionally excited or photoionized. But jets usually create optical signatures, clouds of dust and gas we can photograph. Observations of 3I Atlas have shown some activity, subtle features, but nothing proportional to the radio emission. And jets tend to be messy, irregular, variable. The signal stability we're seeing doesn't match the behavior of known comets. This is where the scientific method shines. One detection is an anomaly. Multiple independent detections become data. By November 8, 2025, the verification picture looks like this. NASA's Deep Space Network confirmed signals on November 2nd and 4th. The 70-meter antenna at Goldstone, California, one of the largest radio telescopes on Earth, pointed at 3I Atlas for 6 hours on November 2nd and detected sporadic pulses matching the 47.3-second periodicity. The detection was weaker than Hayabusa's, expected because Goldstone was farther away and the object had moved, but the timing matched perfectly. The Very Large Array in New Mexico began continuous monitoring on November 3rd. This facility, 27 dish antennas spread across the desert working as a single instrument, has extraordinary sensitivity. Over 72 hours of observation through November 6th, VLA detected strong, consistent signals. Their data confirmed the periodicity to within 0.05 seconds, confirmed the frequency to within 0.05 Hz, and provided directional information showing the source location matches 3I Atlas to within 5 arc seconds, well within the resolution limit. Parkes Observatory in Australia contributed partial confirmation. On November 5th and 7th, during windows when 3I Atlas was above their horizon and scheduling allowed, Parkes detected signals consistent with the reported characteristics. The dataset is smaller, only about 20 pulses total, but they fit the pattern. Not everyone succeeded. ALMA in Chile, potentially the most sensitive instrument for this observation, couldn't participate because 3I Atlas was below the horizon during their optimal windows. Bad luck, wrong geometry. Greenbank Telescope in West Virginia, the largest fully steerable radio dish on Earth, has been down for scheduled maintenance since November 1st, reopening November 10th. Terrible timing. The key point is this: multiple facilities, different technologies, different locations, operated by different teams, all detecting compatible signals. This rules out instrumental artifacts, rules out local interference, rules out mistakes. The signals are real and they're coming from the direction of 3I Atlas. What we need next is more data, longer observation windows, multi-wavelength studies. We need to see if the signals persist as the object moves away from the sun, if they change character, if modulation appears, if anything in the pattern reveals the underlying mechanism. The James Webb Space Telescope has observations scheduled for November 18th through 20th. Infrared imaging that might reveal surface features or thermal signatures. Hubble will image invisible light on November 12th through 14th, looking for jets, coma structure, anything unusual. The science is happening right now, in real time, and we're watching nature, or something else, reveal its secrets one data point at a time. The scientific community doesn't do drama well, at least not publicly. Peer-reviewed papers are written in passive voice, hedged with qualifiers, laden with error bars and confidence intervals. Scientists debate in conference rooms, in journal pages, in careful language that acknowledges uncertainty. But November 2025 is different. The stakes are too high, the implications too profound. And even the most cautious researchers are choosing sides, drawing lines, making arguments with an urgency that betrays the historic nature of this moment. Let's start with the natural explanation camp, because this is where most astronomers instinctively land. When you've spent a career studying the universe and every mysterious signal eventually resolves into mundane physics, you develop a healthy skepticism toward extraordinary claims. Brian Keating, cosmologist at UC San Diego, put it bluntly in a November 6th interview. Plasma physics in cometary environments is astonishingly complex. We barely understand what's happening around solar system comets we've studied for decades. An interstellar comet, formed in a completely different stellar environment with unknown composition and structure, could easily exhibit electromagnetic behavior we've never encountered. Before we start talking about aliens, let's exhaust every natural possibility. The rotating magnetic field hypothesis has serious proponents. Michelle Bannister from the University of Canterbury published a preprint on November 7th outlining how 3I Atlas could possess a strong remnant magnetic field if it formed in a region with intense magnetic flux, perhaps near a young active star with powerful stellar winds. If the object accreted from material already threaded with magnetic field lines, those fields could freeze into the structure as it solidified. We know some asteroids have fields. Psyche, the metal-rich asteroid NASA is currently studying, shows magnetic anomalies. Gaspar and Braille, asteroids visited by spacecraft in the 1990s, both exhibited weak fields. Could 3I Atlas have a field thousands of times stronger? It's not impossible, just unlikely. The rotation rate remains problematic. 47.3 seconds is fast for a large object, creating centrifugal accelerations that approach gravitational binding for a loosely consolidated rubble pile. But perhaps 3I Atlas isn't large. Size estimates are based on brightness and assumed albedo, reflectivity. If the object is unusually dark, absorbing most sunlight, it could be smaller than calculated, maybe only a few hundred meters across rather than several kilometers. A smaller object can spin faster without flying apart. There's precedent. Asteroid 2008, HJ has a rotation period of 42 seconds. Asteroid 2000, D08 rotates in 78 seconds. These are small bodies, tens of meters across, but they prove rapid rotation is possible. The lighthouse mechanism works like this. Magnetic field lines emerge from the object's north magnetic pole, loop through space, and return to the south pole. Charged particles, electrons, and ions from solar wind or from any cometary outgassing get trapped on these field lines, spiral along them, and as they accelerate, they emit synchrotron radiation. If the magnetic axis is tilted relative to the rotation axis, like Earth's magnetic field is offset from its geographic poles, then the emission beam sweeps around as the object rotates. Once per rotation, that beam points at Earth, and we detect a pulse. This is precisely how pulsars work, rotating neutron stars with misaligned magnetic and spin axes, creating cosmic lighthouses visible across the galaxy. But here's where the hypothesis strains: the frequency. Synchrotron radiation from particles spiraling in magnetic fields produces a broad spectrum, not a narrow line. The emission spans from radio through optical, depending on particle energy and field strength. To get strong emission specifically at 1.42 GHz requires either an extraordinary coincidence, the parameters just happen to peak at that frequency, or some kind of resonant cavity effect that amplifies one frequency over others. Neither seems likely, but not impossible. The plasma oscillation hypothesis takes a different approach. Forget magnetic fields. Focus on the coma, the cloud of gas and dust surrounding any active comet. When solar wind, moving at 400 kilometers per second, crashes into this relatively stationary cloud, it creates a bow shock, a boundary where the supersonic flow becomes subsonic. Within this shock region, plasma becomes compressed, heated, turbulent. Plasma can support oscillations, waves of charge density that propagate through the medium. The natural frequency of these oscillations depends on electron density. Specifically, the plasma frequency is proportional to the square root of density. For emission at 1.42 GHz, you need an electron density of about 25 million electrons per cubic centimeter. That's higher than typical cometary comas, but not impossible near the nucleus, where gas density is greatest. If conditions are right, if the shock region has the correct geometry and density profile, plasma oscillations could amplify through a feedback mechanism, becoming coherent, mode-locked, emitting at a specific frequency. The periodicity comes from rotation modulating this process, perhaps varying the shock strength or the viewing angle. Paul Kalis from Berkeley, who discovered the debris disk around Fomalhaut and studies dusty environments, suggests the coma might form a resonant cavity. If dust particles become charged, as they do in space when photoelectrons are knocked off by ultraviolet light, and if these charged particles arrange themselves in layers due to electrostatic forces, you could create a structure that traps electromagnetic waves. Like an organ pipe that resonates at specific frequencies determined by its length, a plasma cavity resonates at frequencies determined by its size and density. The hydrogen line frequency, corresponding to a 21 centimeter wavelength, would resonate in a cavity about 10 centimeters across, accounting for plasma's effect on wave speed. A coma filled with such microstructures, all oscillating in phase because they're driven by the same solar wind pressure, could collectively emit coherent radiation. It's creative. It's theoretically possible. But it requires exquisite fine-tuning. Natural systems tend toward disorder, not precision. Getting millions of dust grains to cooperate to maintain a stable density profile that keeps the resonance at exactly 1.42 gigahertz over hours, while the comet rotates and the solar wind buffets it, strains credulity. Yet nature has surprised us before. Quantum mechanics predicts absurdly specific energy levels in atoms, and atoms obey those predictions with perfect precision across the entire universe. Perhaps plasma structures can exhibit similar quantization under the right conditions. Then there's the outgassing jet hypothesis, championed by researchers who study active comets. Jets are common. When sunlight heats a comet's surface, ice sublimates, turning directly from solid to gas without melting. This gas expands rapidly, carrying dust particles, creating visible features we can photograph. Comet Hartley 2, visited by NASA's Deep Impact spacecraft in 2010, showed beautiful jets streaming from active regions. Comet 67P, studied extensively by ESA's Rosetta mission from 2014 to 2016, exhibited complex jetting patterns that change with rotation and solar illumination. If 3I Atlas has a jet, and that jet contains atomic hydrogen from dissociated water molecules or methane or ammonia, then the hydrogen atoms could emit at the 21 centimeter line if they're excited by solar ultraviolet radiation or by collisions in the dense gas flow. As the nucleus rotates every 47.3 seconds, the jet sweeps around, and when it points toward Earth, we see enhanced emission. The pulse duration, 2.7 seconds, represents how long the jet stays in our line of sight during each rotation, about 5% of the rotation period, suggesting a fairly narrow jet cone. The problem is visibility. Jets that produce strong radio emission should also produce optical emission, scattered sunlight from dust, fluorescence from excited molecules. Observers have looked. Images of 3I Atlas taken in late October and early November show some faint features, possibly a weak coma, but nothing spectacular, nothing proportional to the radio emission. It's possible the gas is unusually dust-poor, or the dust is so dark it doesn't scatter much light, but these are additional assumptions piled onto the hypothesis. Every natural explanation requires something unusual, something we haven't seen before, some combination of conditions that just barely works if you tune the parameters correctly. Individually, each mechanism is plausible. Collectively, they feel forced, like explaining a pattern in clouds by invoking precisely shaped ice crystals that just happen to form a recognizable image. Possible? Yes. Likely? That's where opinions diverge. Now let's examine the artificial explanation, the hypothesis that the signals are technological, that 3I Atlas is not a natural object but a probe, an artifact, something built and sent by an intelligence not our own. This is where Avi Loeb stands, and he's not alone, though he's the most vocal. Loeb's argument is statistical. On November 5th, he published his paper calculating probabilities. The hydrogen line frequency is one specific value out of millions of possible frequencies across the radio spectrum. The probability that a random natural process produces emission at exactly this frequency within 0.01 Hz is roughly 1 in 10 million. The probability that a natural process produces periodic signals with 0.8% timing stability is perhaps 1 in 1,000, being generous. The probability that both occur simultaneously, that you get hydrogen line emission with precise periodicity, is the product. 1 in 10 billion. When the probability of coincidence drops this low, Loeb writes, we must consider intentionality. The intentional beacon hypothesis proposes that 3I Atlas is transmitting deliberately, announcing its presence to any civilization capable of detecting radio signals. The frequency choice is obvious. The hydrogen line is the universal channel, the frequency any radio astronomer would monitor. The periodicity could encode information. 47.3 seconds might not be arbitrary. It's close to 15 times pi, which is 47.12 seconds. Pi is a mathematical constant, recognizable to any technological species. Is 3I Atlas broadcasting pi? The timing uncertainty, plus or minus 0.2 seconds, makes this ambiguous, but it's suggestive. The power requirement is minimal. Half a watt of radiated power, less than a flashlight, detectable across interplanetary distances because space is so empty, because background noise is so low. If you wanted to operate a beacon for millions of years, minimizing power consumption would be essential. A small nuclear battery, a radioisotope thermoelectric generator like those powering Voyager 1 and 2 for over 45 years, could easily provide half a watt continuously. Why beacon after billions of years traveling? Perhaps the probe was programmed to activate near stars, to conserve power in interstellar space and wake up when approaching a stellar system. The perihelion passage on October 30th, when 3I Atlas came within 1.4 astronomical units of the Sun, could have triggered activation. Solar panels charging batteries, thermal sensors detecting increased temperature, proximity sensors recognizing a stellar environment, any of these could initiate transmission protocols. Alternatively, the signals might not be intentional communication, but leakage radiation, electromagnetic emissions from internal systems. Every human spacecraft leaks radio waves, byproducts of electronics, power distribution, data processing. If 3I Atlas has active systems, a functional computer, sensors, attitude control, those systems might emit detectable radiation. The 47.3-second periodicity could be a clock cycle, a control loop, a scanning sequence. The hydrogen line frequency could be coincidental, or it could be the operating frequency of some component, chosen for engineering reasons that happen to align with nature's universal constant. Jason Wright, astronomer at Penn State who studies technosignatures, points out that leakage radiation would likely be weaker and more variable than intentional transmission. The signal strength we're seeing, weak but stable, fits intentional transmission better. He also notes the narrow bandwidth, the clean sine wave, the consistent polarization, all characteristics of engineered signals rather than noisy electronics. The attitude control hypothesis, proposed by researchers at MIT, suggests the pulses are related to the non-gravitational acceleration that's been separately reported for 3I Atlas. If the object is using electromagnetic propulsion, perhaps an ion drive or a plasma thruster, those systems would emit radio waves as a side effect. The 47.3-second cycle could be thruster firings, brief pulses of thrust to maintain orientation or adjust trajectory. The hydrogen line frequency might emerge from the ionization process if the propellant is hydrogen. But this faces a challenge. The signal strength seems weak for propulsion. Ion drives that produce measurable thrust require kilowatts of power. The radio emission we're detecting corresponds to half a watt. Unless the propulsion is extraordinarily efficient, or unless we're only seeing a tiny fraction of the total emission because most of it beams in other directions, the numbers don't quite match. Understanding whether 3I Atlas's signals are natural or artificial requires understanding what electromagnetic phenomena naturally occur in space, what precedents exist, what nature is capable of producing without any intervention from intelligence or technology. The universe is not quiet. It crackles and hums and roars across the electromagnetic spectrum, from radio waves meters long to gamma rays smaller than atomic nuclei. Every star, every planet with a magnetic field, every gas cloud, every exploding supernova contributes to the cosmic cacophony. So let's examine what nature does, and then assess whether 3I Atlas fits those patterns. Jupiter, the gas giant, was humanity's first encounter with natural radio emissions from another planet. In 1955, radio astronomers Bernard Burke and Kenneth Franklin, using an 18-meter antenna in Maryland, detected powerful bursts of radio waves coming from Jupiter at frequencies around 20 megahertz. They initially thought it was terrestrial interference, maybe lightning storms or military radar, but the signals repeated with Jupiter's 10-hour rotation period. The source was clearly Jupiter itself. We now understand the mechanism. Io, Jupiter's innermost large moon, orbits through Jupiter's intense magnetic field, generating electric currents that flow along field lines into Jupiter's polar regions. These currents accelerate electrons, which spiral around magnetic field lines and emit synchrotron radiation, creating radio bursts detectable across the solar system. The emissions are periodic because they're modulated by Io's orbit and Jupiter's rotation, but they're also variable, influenced by solar wind pressure, volcanic activity on Io, the complex dynamics of plasma in Jupiter's magnetosphere. Compare that to 3I Atlas. Jupiter's radio emissions span megahertz of bandwidth, broadband noise with some structure, but fundamentally chaotic. The signals we're detecting are narrowband, less than 1 hertz wide, 6 orders of magnitude more focused. Jupiter's emissions vary in strength by factors of 10 or more from burst to burst. 3I Atlas's signals are stable to within a few decibels over hours. Jupiter has a planet-sized magnetic field powered by internal convection, a dynamo driven by metallic hydrogen under immense pressure. 3I Atlas is a small body, no internal power source, no mechanism to generate such organized fields. The comparison doesn't hold. Pulsars, discovered by Jocelyn Bell Burnell in 1967, represent nature at its most astonishingly regular. Bell, then a graduate student at Cambridge, was using a radio telescope to study quasars when she noticed signals that pulsed with perfect regularity, 1.327 seconds between pulses, repeating hour after hour, day after day, with a stability that rivaled atomic clocks. The Discovery team half-jokingly called the source LGM-1, Little Green Men 1, because the signals seemed too regular to be natural. But they were natural. The source was a pulsar, a neutron star, the collapsed core of a massive star that exploded as a supernova, now compressed to 20 kilometers diameter, spinning rapidly, sweeping beams of radio emission across space like a cosmic lighthouse. Pulsars rotate from milliseconds to seconds, their periods extraordinarily stable because they're rotating stars. And stars have enormous angular momentum that doesn't dissipate quickly. 3I Atlas's 47.3-second period is slower than most pulsars, but not outside the range. The oldest pulsars, having slowed over millions of years as they radiate energy, can have periods of several seconds. But pulsars are neutron stars, objects with masses greater than the sun compressed into city-sized volumes, with magnetic fields of 1 trillion Gauss. They're the most extreme objects in the universe, short of black holes. Applying the pulsar analogy to a small comet or asteroid requires explaining how such a modest object generates coherent beams, maintains rotational stability, and emits at a specific frequency rather than broadband spectrum. The physics doesn't scale. Solar radio bursts offer another natural phenomenon. The sun constantly emits radio waves, especially during flares and coronal mass ejections. Type their through. Solar radio bursts occur when beams of electrons accelerated by magnetic reconnection travel through the solar corona, exciting plasma oscillations that emit radio waves at the local plasma frequency. These bursts sweep downward in frequency as the electrons move outward through decreasing density plasma, creating characteristic signatures on radio spectrograms. They're intense, brief, broadband, and clearly associated with violent solar activity. Nothing about 3I Atlas resembles this. The object is not a star, has no corona, no magnetic reconnection, no electron beams accelerated to near light speed. Cometary radio emissions do exist, though they're rare and weak. When the Giotto spacecraft flew past Comet Halley in March 1986, instruments detected radio waves in the frequency range from tens of kilohertz to several megahertz. The emissions were attributed to plasma waves in the comet's interaction region with solar wind, turbulence generating Langmuir waves and ion acoustic waves that converted to electromagnetic radiation. The European Space Agency's Rosetta mission, which orbited Comet 67P from 2014 to 2016, detected radio emissions at frequencies up to several hundred kilohertz. These were irregular, variable, broadband, associated with outgassing events and plasma instabilities. Nothing like the narrowband, stable, periodic signals from 3I Atlas. Fast radio bursts, FRBs, discovered in 2007 were initially mysterious. These are millisecond duration pulses of radio emission coming from distant galaxies, releases of energy equivalent to what the sun emits over days, compressed into a fraction of a second. For years, explanations ranged from colliding neutron stars to alien signals. In 2020, the mystery was solved when an FRB was detected from a known magnetar, a neutron star with an ultra-strong magnetic field, in our own galaxy. The bursts are now understood as natural phenomena, extreme astrophysics involving objects we barely comprehend. But FRBs are extragalactic, billions of light years away. 3I Atlas is here in our solar system, 250 million kilometers away. The comparison is irrelevant. The precedents don't fit. Natural radio emissions in space are either broadband and chaotic, like Jupiter and solar bursts, or narrowband and associated with extreme objects like pulsars and magnetars. Comets do emit, but weakly and irregularly, nothing approaching the characteristics of 3I Atlas's signals. Which brings us to the hydrogen line itself, the 21-centimeter radiation that's central to this mystery. The hydrogen line arises from a quantum mechanical process. A hydrogen atom consists of one proton and one electron. Both have spin, an intrinsic angular momentum. When the electron's spin aligns parallel to the proton's spin, the atom has slightly more energy than when the spins are anti-parallel. The energy difference is tiny, corresponding to a photon with a wavelength of 21.106 centimeters, or a frequency of 1.42405752 megahertz. Occasionally, spontaneously, an atom in the higher energy state flips to the lower state, emitting a photon at this exact frequency. The transition is forbidden by selection rules, so it's extremely rare. Any individual hydrogen atom flips once every 11 million years on average. But space contains so much hydrogen, vast clouds of neutral atomic hydrogen in interstellar space, that collectively they emit detectable 21-centimeter radiation. Radio astronomers map the galaxy by detecting hydrogen line emission. The radiation reveals where gas clouds are, how dense they are, how fast they're moving based on Doppler shifts. It's fundamental observational astronomy, the way we trace spiral arms and galactic structure. But the emission from these clouds is broadband, spread over several kilohertz because atoms are moving, creating Doppler broadening, and because magnetic fields split the energy levels slightly, creating fine structure. Natural hydrogen line emission is never as narrow as what we're seeing from 3I Atlas. Could 3I Atlas have a cloud of cold atomic hydrogen, atoms moving so slowly that Doppler broadening is minimal, all emitting coherently at exactly the same frequency? Theoretically, yes, if the temperature is near absolute zero and the density is just right. But such conditions don't exist around comets. Comets are hot, heated by sunlight, with gas temperatures of hundreds or thousands of Kelvin, atoms moving at kilometers per second, creating substantial Doppler broadening. Getting a natural hydrogen cloud to emit a signal as narrow as observed requires physics that doesn't apply in cometary environments. This is why the frequency precision troubles scientists. It's why even skeptics admit the observations are unusual. Nature is capable of extraordinary things, but nature doesn't usually tune itself to human-defined standards. The hydrogen line isn't arbitrary to us because we've studied hydrogen, built our physics around it, designated it as special. But to a comet, to a plasma cloud, to any natural astrophysical process, there's nothing special about 1.42 gigahertz. It's just another frequency. For 3I Atlas to emit at this exact frequency, within 1 part in 100 million, requires either a staggering coincidence or a reason. A mechanism that selects this frequency specifically. If the signal is artificial, the frequency choice is obvious. Any technological civilization that develops radio astronomy will discover the hydrogen line. It's the most abundant element, its emission is universal, it's a natural standard. If you want to be heard, if you want your signal recognized as artificial rather than dismissed as natural background, you broadcast at the hydrogen line. It says, "We know physics, we understand the universe. This is intentional." It's the cosmic equivalent of prime numbers or mathematical constants, a beacon that screams intelligence to anyone listening. But if the signal is natural, we need a new phenomenon, a plasma process or resonance or electromagnetic mechanism that hasn't been observed before, that produces narrowband emission at a frequency that just happens to match the most significant line in radio astronomy. The probability is low, but low probability isn't impossibility. The universe is large, contains multitudes, and we've only studied a tiny fraction of it. Perhaps 3I Atlas represents a new category of object, interstellar comets with properties we've never encountered, exhibiting physics that will expand our textbooks and challenge our models. That would be extraordinary. It would be a discovery worthy of Nobel consideration. But it would be natural, explicable, ultimately understandable within the framework of known physics, even if the details are currently mysterious. Or perhaps it's not natural. Perhaps we're witnessing something that requires expanding our framework, not just of physics, but of biology, of intelligence, of what exists in the universe beyond Earth. That too would be extraordinary. That too would merit Nobel Prizes, reshape civilization, rewrite history. The question is, which extraordinary explanation is correct? The data will decide, not our preferences, not our hopes or fears. The electromagnetic pulses will either resolve into natural phenomena as observations accumulate, or they'll resist natural explanation persistently enough that the alternative becomes unavoidable. We're living through that process right now in November 2025, watching science work the way it's supposed to, testing hypotheses against reality and waiting to see what reality reveals. If the signals are natural, if 3I Atlas turns out to be a comet with exotic electromagnetic properties driven by plasma physics we don't yet fully understand, the scientific impact is still profound. We'll have discovered a new emission mechanism, a phenomenon that exists nowhere in our textbooks, that requires updating models of how comets interact with their environment, how magnetic fields and rotation and solar wind conspire to produce coherent radio waves. Graduate students will write dissertations analyzing the plasma dynamics. Theorists will develop new equations describing the resonance conditions, the feedback mechanisms, the stability requirements. Observational astronomers will search for similar signatures from other comets, other asteroids, wondering if 3I Atlas represents a class of objects we've simply never detected before because we weren't looking in the right way with the right instruments at the right time. The discovery would validate the importance of multi-wavelength astronomy, the practice of observing celestial objects not just in visible light but across the entire electromagnetic spectrum. Radio, infrared, ultraviolet, X-rays, gamma rays. Each wavelength reveals different physics, different processes, different phenomena. Hayabusa's plasma wave analyzer wasn't designed to revolutionize astrophysics. It was meant to study asteroid environments, measure particle densities, characterize space weather. But because it was there, because it was sensitive to radio frequencies, because controllers happened to turn it on at the right moment, we detected something extraordinary. Serendipity in science isn't luck. It's preparedness meeting opportunity. It's having instruments capable of seeing the unexpected and having scientists alert enough to recognize anomalies when they appear. Public engagement matters too. Even if 3I Atlas resolves into natural phenomena, the excitement it's generated, the global attention, the conversations happening in classrooms and coffee shops and comment sections, these represent Science communication at its best. People are paying attention to astrometry, to plasma physics, to interstellar objects. They're learning about radio astronomy, about the hydrogen line, about how science works through observation and hypothesis testing. When the final explanation emerges, natural or otherwise, millions will understand not just the conclusion, but the process, the rigorous methodology, the international cooperation, the peer review, the healthy skepticism balanced with open-mindedness. That's a victory for scientific literacy, for public understanding, for the culture of curiosity that drives progress. But if the signals are artificial, if every natural explanation fails and we're forced to conclude that 3i Atlas is technological, an artifact constructed by intelligence not of this earth, then everything changes. Not gradually, not eventually, immediately and irrevocably. The confirmation alone, the moment when scientific consensus shifts from probably natural to likely artificial, represents the most significant event in human history, bar none. The invention of agriculture, the Industrial Revolution, the atomic age, the internet, all pale compared to the discovery that we are not alone, that intelligence exists elsewhere, that someone else built something and sent it through the cosmos and it's here now. Transmitting, announcing presence, confirming that the universe contains minds other than our own. Who built it? That's the first question everyone asks, the most natural question, and also potentially the most unanswerable. The object is traveling at 60 kilometers per second relative to the sun, fast enough to be unbound, which means it's been coasting through interstellar space for a very long time. At that velocity, traveling from the nearest star system, Alpha Centauri 4.37 light-years away, would take about 22,000 years. But Alpha Centauri probably isn't the origin. The object's trajectory doesn't point back there. Tracing the path backward, accounting for the sun's motion and the galaxy's rotation, 3i Atlas could have originated from anywhere within hundreds of light-years, from any of thousands of star systems, and the journey could have taken anywhere from tens of thousands to millions of years, depending on origin distance and launch velocity. The civilization that built it might still exist, thriving, expanding, perhaps wondering if their probe has encountered anything interesting lately, or they might be extinct, their species dead, their planets cold, their star perhaps itself gone dark or exploded, leaving only their artifacts drifting through the galaxy as tombstones, epitaphs, messages in bottles cast into the cosmic ocean billions of years ago. The probe could be older than human civilization, older than humanity itself, could have been launched when Earth's continents were arranged differently, when dinosaurs still walked, when our ancestors were tiny mammals hiding in burrows. There's no way to know without more information, without somehow accessing the probe's memory, its data storage, its purpose. The message interpretation challenge is immediate. Right now, the signal appears to be a simple carrier wave, unmodulated, no information content beyond its existence, its frequency, its timing. But analysis is ongoing. Teams at SETI institutes worldwide are applying every signal processing technique known to science, looking for subtle amplitude variations, phase shifts, frequency deviations, anything that might encode data, binary patterns in the timing, mathematical sequences in the pulse intervals, modulation so sophisticated it requires advanced algorithms to detect. If information is there, if the probe is trying to communicate rather than simply announce, decoding it becomes humanity's most urgent intellectual challenge. The 47.3-second periodicity might itself be meaningful. It's close to 15 times pi, 47.12 seconds if you use pi to 6 decimal places. Is that coincidence or deliberate? Pi is universal, a mathematical constant that any technological species would recognize. The ratio of circumference to diameter in a circle emerges from geometry itself, independent of units or culture or biology. If you want to say we understand mathematics, broadcasting a signal timed to pi is one way to do it. But the 0.2-second uncertainty in the measurement makes this ambiguous. Is it exactly 15 pi and we're just not measuring precisely enough? Or is it 47.3 seconds for some other reason? Perhaps the rotation period of the probe, the cycle time of its systems, a frequency chosen for engineering convenience that has nothing to do with mathematical constants? Response protocols exist, debated and refined over decades by the SETI community. The post-detection protocol established in 2010 outlines steps to follow if we detect an extraterrestrial signal. First, verify thoroughly. Eliminate all possible false positives. Second, inform other qualified observers. Allow independent confirmation. Third, notify relevant authorities, including the Secretary General of the United Nations and the International Astronomical Union. Fourth, after confirmation, make a public announcement through scientific channels. Fifth, and this is crucial, do not respond. Do not transmit anything back until international consultation establishes consensus on whether and how to reply. That last point is controversial. METI, messaging to extraterrestrial intelligence, has been debated for years. Some argue we should actively transmit, announce our presence, send information about Earth and humanity into space. Others, including prominent scientists like Stephen Hawking before his death, warned that broadcasting our location might be dangerous, that we have no idea what's out there, whether advanced civilizations are friendly or hostile, whether revealing ourselves invites contact or conquest. The dark forest hypothesis, popularized by Liu Cixin's science fiction trilogy, suggests the Stu-Junian universe might be filled with civilizations hiding from each other, staying silent to avoid detection by potential predators, and that anyone who broadcasts gets targeted and destroyed. If 3i Atlas is confirmed artificial, the dark forest debate becomes immediate and practical. The probe already knows we're here, or will soon. It's in our solar system. If it has sensors, it can detect our radio and television broadcasts, our radar emissions, the electromagnetic signature of technological civilization leaking into space. Staying silent at this point might be meaningless, or perhaps the probe isn't listening, isn't interested in us, is simply following ancient programming, executing a mission designed millions of years ago, broadcasting its beacon indifferently, not caring whether anyone hears or responds. Geopolitical dynamics complicate everything. Currently, November 2025, the response to 3i Atlas has been remarkably cooperative. JAXA discovered it, NASA and ESA confirmed it, data is being shared openly, scientists worldwide are collaborating. But that's the scientific community, researchers who've worked together for decades, who value openness and transparency, who see 3i Atlas as a question to answer rather than a resource to exploit. Governments think differently. Military and intelligence agencies think differently. If the object is confirmed technological, national security concerns activate immediately. Does the probe contain technology we could reverse engineer? Propulsion systems more efficient than ours? Energy sources we haven't invented? Materials with properties we don't understand? The strategic advantage to whoever retrieves and studies such technology could be enormous, decisive, civilization-altering. Suddenly, 3i Atlas isn't just a scientific curiosity. It's a prize, a treasure, something nations might compete for, might fight over if the opportunity to capture it existed. Right now, that opportunity doesn't exist. The object will pass Earth at 250 million kilometers in mid-December, far too distant for any intercept mission with current technology. Even if we launched a spacecraft today, the fastest probe we could build, using gravitational assists and every trick in the orbital mechanics playbook, couldn't reach 3i Atlas before it exits the inner solar system and heads back into interstellar space. By 2027, it'll be beyond Neptune's orbit. By 2030, beyond the heliopause, the boundary where solar wind yields to interstellar medium. We had one chance and we missed it, didn't even know the object existed until it was already approaching perihelion, already too late for intercept. But future visitors might be detected earlier, with more warning when intercept missions are feasible. The Vera Rubin Observatory, which began operations in 2024, surveys the entire southern sky every few nights, detecting asteroids, comets, anything moving. Future interstellar objects will be spotted months or years in advance, giving time to plan. To launch, to send spacecraft. If 3i Atlas confirms that technological artifacts traverse the galaxy, then detecting and studying such artifacts becomes a priority, and the first nation to successfully retrieve one gains incalculable advantages. That reality will shape space policy, military planning, international relations for decades. Public reaction is already showing the full spectrum of human response to the unknown. Polls from November 6th and 7th, conducted across multiple countries, show 42% of respondents believing the signals are artificial, 31% natural, 27% unsure. Those numbers are surprisingly stable across demographics. Education level matters less than you'd expect. People with advanced degrees are only slightly more skeptical than those with high school education. Age shows some correlation, younger people more likely to believe artificial origin, older people more cautious, but the differences are modest. What matters more is worldview, whether people are predisposed to trust scientific authority or question it, whether they're optimistic about the universe or pessimistic, whether the idea of alien contact excites or frightens them. Social media is predictably chaotic. Twitter trends show 3i Atlas and First Contact competing for attention. Reddit communities are inundated with posts, speculation, arguments, memes. YouTube channels are generating content at extraordinary rates, some responsible, many sensationalist, a few deliberately misleading. Conspiracy theories proliferate. The government has known for months and covered it up. The probe has already communicated and authorities are hiding the message. The signals contain warnings about imminent danger. The probe is observing Earth and selecting targets. None of these claims have evidence. All of them spread faster than corrections. Misinformation is the shadow pandemic accompanying the discovery. False claims that 3i Atlas is approaching Earth, that it'll arrive in December and impact, that it's transmitting mind control signals, that it's caused earthquakes or weather anomalies, all demonstrably false, all circulating widely. Fact-checkers are overwhelmed. Organizations like Snopes, factcheck.org, media literacy groups are issuing clarifications constantly. NASA and JAXA have both released public statements emphasizing that the object poses no threat, that it will pass at a safe distance, that the signals are being studied scientifically, that speculation ahead of data is unhelpful. Religious institutions are responding with surprising calmness. The Vatican issued a statement on November 6th noting that Catholic theology has no problem with extraterrestrial life, that God's creation could easily extend beyond Earth, that discovering other intelligences would be a cause for wonder and gratitude, not crisis. Islamic scholars have noted that the Quran mentions God creating beings in the heavens and earth, and that nothing in Scripture prohibits life elsewhere. Protestant. Denominations vary, some fundamentalist groups troubled by implications for human uniqueness, most mainstream churches echoing the Vatican's openness. The Dalai Lama, asked about 3i Atlas during a November 5th interview, smiled and said, "If there are others in the universe practicing compassion, that is wonderful. If they need to learn compassion, perhaps we can help each other." Economic impacts are already visible. Stock markets showed brief volatility on November 1st when NASA confirmed the signals, but stabilized quickly. Space industry companies SpaceX, Blue Origin, Rocket Lab saw share prices increase 3.8% over the first week of November as investors anticipated increased interest in space exploration. SETI-related organizations saw donation surges, the SETI Institute reporting a 400% increase in contributions between November 1st and 7th. Universities offering astrobiology programs are experiencing record enrollment inquiries for next academic year. The cultural zeitgeist is shifting, attention focusing upward, outward, toward the cosmos and what it might contain. What happens next, in the immediate term, depends entirely on observations over the coming weeks. The trajectory of 3i Atlas is fixed, governed by gravity and momentum. It will reach closest approach to Earth around December 19th at approximately 250 million kilometers, about 1.67 astronomical units. That's far, almost twice the Earth-Sun distance, no risk of impact, no danger, just an opportunity for enhanced observation as geometry improves. Every major telescope is scheduled to observe. Hubble on November 12th through 14th will image invisible and ultraviolet wavelengths, looking for surface features, coma structure, jets, anything optical telescopes can reveal. The James Webb Space Telescope observes November 18th through 20th in infrared, probing thermal signatures, temperature distribution, possibly compositional clues from spectroscopy. Radio observatories continue constant monitoring, the Very Large Array. Parks, the Deep Space Network, listening for any change in the signal, any modulation, any deviation from the established pattern. By late December, 3i Atlas will be receding, moving outward past Mars' orbit, fading from optimal observation windows. The signals might persist, might weaken, might stop entirely as the object moves farther from the Sun. If they stop, correlation with solar distance would suggest natural emission driven by solar heating or solar wind interaction. If they persist unchanged, that's a mark toward artificial origin, a beacon operating independently of environmental conditions. Either outcome constrains the hypothesis space, narrows possibilities, brings us closer to understanding. We are here now, November 8th, 2025, 11 days after the initial detection, living through a moment that might be historic or might be merely interesting, and we won't know which until more data resolves the ambiguity. Let's establish exactly where we stand, what's confirmed, what remains uncertain, and what you should watch for over the coming weeks as this story continues to unfold in real time. The timeline is compressed and intense. July 1st, 3i Atlas, discovered by Atlas Survey telescopes in Chile, initially cataloged as another near-Earth asteroid until orbital calculations revealed hyperbolic trajectory, interstellar origin confirmed within days. July through October, astronomers tracked it, refined the orbit, calculated perihelion date, noted some unusual features, but nothing extraordinary, just another interstellar visitor following Oumuamua and Borisov. October 28th, everything changed. Hayabusa's plasma wave analyzer detected the pulses, 6 hours of data captured before the observation window closed. October 30th, perihelion, closest approach to Sun at 1.4 astronomical units, the moment when solar heating reaches maximum, when any cometary activity should peak. October 31st, JAXA completed verification and released their carefully worded statement, triggering the global response. November 1st and 2nd, NASA's Deep Space Network confirmed detection, independent verification establishing the signals are real. November 3rd, JAXA released preliminary data publicly, opening analysis to the worldwide scientific community. November 4th through 7th, additional observatories contributed observations, the Very Large Array accumulating 72 hours of high-quality data, Parkes Observatory capturing partial confirmation. November 5th, Avi Loeb published his analysis arguing for technological origin based on frequency precision and timing stability. November 7th, JAXA released the full dataset, raw numbers available for anyone to download and analyze. November 8th, today, we have multiple confirmations, broad consensus that the signals are real and originate from 3i Atlas, zero consensus on what they mean. The scientific community's position, surveyed informally by Sky and Telescope magazine on November 6th and 7th, shows 45% favoring exotic natural plasma phenomena, 30% supporting rotating magnetic field hypotheses, 15% considering technological origin seriously, 7% proposing combined mechanisms, and 3% admitting uncertainty and demanding more data. These aren't formal votes. Science doesn't work by democracy, but they represent the distribution of informed opinion among 847 professional astronomers who responded, a snapshot of where expert thinking currently stands. What's confirmed beyond reasonable doubt? The electromagnetic pulses are real, detected by multiple independent facilities using different instruments. The source location matches 3i Atlas to within observational resolution. The frequency is 1.420405752 MHz within 0.01 Hz of the hydrogen line. The periodicity is 47.3 seconds plus or minus 0.2 seconds, extraordinarily stable over the 6-hour initial observation and subsequent confirmations. The signal strength is weak but measurable, approximately negative 87 dBm, corresponding to roughly half a watt radiated power if emission is isotropic. The pulses are not instrumental artifacts, not terrestrial interference, not mistakes or misinterpretations. They exist, they're coming from that location in space, and they require explanation. What remains uncertain? Everything else. The mechanism producing the signals is unknown. Natural processes haven't been ruled out, but they're strained, requiring combinations of conditions and parameters that seem improbable, though not impossible. Artificial origin remains speculative, supported by circumstantial evidence like frequency precision, but lacking definitive proof like modulation or information content. We don't know if the signals will persist, will change, will stop. We don't know if they correlate with solar distance, with rotation, with any other observable parameter. We don't know the object's composition, its structure, whether it has a magnetic field, what its surface looks like, whether it's actively outgassing. We have radio data and limited optical observations, a narrow slice of information from which we're trying to infer the nature of an object that traveled potentially millions of years to reach us. The observation campaign intensifies now. Hubble's scheduled observations November 12th through 14th will provide the highest resolution optical images yet obtained. Hubble can potentially resolve surface features if the object is large and reflective, can detect coma structure if gas and dust are present, can measure color and brightness variations that constrain composition and rotation. The James Webb Space Telescope follows November 18th through 20th with infrared imaging, probing thermal emission, seeing heat signatures invisible to optical telescopes. JWST's spectrometer can analyze reflected sunlight and thermal emission simultaneously, identifying molecules, distinguishing ice from rock, characterizing the surface and any surrounding material. These observations are critical. If they show normal cometary features, extensive coma, active jets, spectroscopic signatures of volatiles like water and carbon monoxide, then natural explanations gain support. If they show minimal activity, a bare nucleus, no obvious gas emission despite the radio pulses, natural explanations face difficulties. Radio monitoring continues without pause. The Very Large Array maintains its observing program, accumulating data night after night, watching for any change in signal characteristics. If modulation appears, if the carrier wave starts varying in amplitude or frequency, if patterns emerge in the timing, that's front-page news immediately. If the signal strengthens or weakens systematically, correlation analysis can test whether it's driven by solar distance, by rotation, by other factors. If the signal stops abruptly, that's also informative, suggesting whatever mechanism was operating has ceased, perhaps because conditions changed, perhaps because power ran out, perhaps because the beacon completed its programmed transmission sequence. The Breakthrough Listen initiative, funded by Yuri Milner's Breakthrough Prize Foundation, has designated 3i Atlas as a priority target. Their observing time on major radio telescopes worldwide, including Parkes Observatory and the Green Bank Telescope, once it returns from maintenance on November 10th, will be directed toward the object. Breakthrough Listen specializes in searching for technosignatures, and their analysis pipelines are optimized for detecting structured signals, patterns, anything suggesting information content. If anyone can find modulation or encoding in the pulses, it's them. Amateur radio astronomers are also involved. The signal is weak, requiring sensitive equipment and careful integration time, but it's not impossible for well-equipped amateur stations to detect. Several have succeeded, posting their results online, contributing to the verification, demonstrating the democratization of astronomy. You don't need a billion-dollar facility to participate in this discovery. You need knowledge, dedication, decent equipment, and clear skies. Citizen science at its finest. How should you follow along? Official sources remain the gold standard. JAXA updates its mission pages every 48 to 72 hours with new information about observations and data releases. NASA's Jet Propulsion Laboratory maintains the Small Body Database, tracking 3I Atlas's orbit with daily refinements. The European Space Agency coordinates multi-facility observations and posts summaries of findings. These agencies have reputations to protect: peer review processes, institutional caution that prevents premature conclusions, trust them over social media speculation. Scientific preprint servers, particularly archive.org in the astronomy section, host papers before peer review. Researchers submit manuscripts describing observations, analyses, hypotheses, and these appear online within days of submission. Read them, but read critically. Preprints haven't been vetted by peer reviewers, haven't survived the scrutiny that weeds out errors and overstatements. Some will be correct, some will be wrong, some will be interesting but inconclusive. Learning to evaluate scientific claims, to distinguish strong evidence from weak speculation, is a skill worth developing, and this situation offers real-time practice. Reliable science journalists exist. They're rarer than they should be, but they're out there. Publications like Sky and Telescope, Scientific American, Nature News, Science Magazine's news section. These employ journalists with scientific training who understand the topics, who interview experts, who report accurately. Space.com generally does good work, though occasionally they lean toward sensationalism. Avoid tabloids. The New York Post might be entertaining, but their headlines outpace their accuracy. If a claim sounds too dramatic, too certain, too perfectly aligned with narrative rather than evidence, verify it through primary sources before believing. Social media requires extreme caution. Twitter, now X, hosts many professional astronomers sharing insights, posting updates, explaining concepts. Follow verified accounts like Avi Loeb, Phil Plett, the Bad Astronomer, Katie Mack, official SETI Institute accounts, but also recognize that social media rewards engagement over accuracy, that sensational claims spread faster than corrections, that you'll encounter misinformation constantly. Critical thinking is essential. Ask yourself, what's the source? What's the evidence? Does this align with what official agencies are saying? Am I believing this because it's true or because I want it to be true? The bigger picture, the reason this matters regardless of outcome, transcends the specific question of whether 3I Atlas is natural or artificial. We're witnessing the scientific method in action: hypothesis generation and testing, international cooperation, data sharing, transparent debate. This is how science should work, and seeing it work in real time under global scrutiny with stakes this high demonstrates the process's power and integrity. We're also confronting the limits of knowledge, the reality that some questions can't be answered immediately, that uncertainty persists until evidence accumulates sufficiently. That's uncomfortable for a species that craves certainty, but it's honest, it's real, and it's how we ultimately arrive at truth. The universe is vast, containing approximately 200 billion trillion stars, 2 followed by 23 zeros, each potentially hosting planets, some of those planets potentially harboring life, some of that life potentially developing intelligence, some of that intelligence potentially building technology, some of that technology potentially including interstellar probes. The numbers suggest we shouldn't be alone. The Fermi paradox asks why we don't see evidence of others if they're out there. Maybe we do see evidence now. Maybe 3I Atlas is the first confirmed example of what statistics predict should exist. Or maybe it's a comet with weird plasma physics, and the search continues. Either way, the object reminds us to look up, to question, to wonder. Whether it's nature revealing new physics or intelligence announcing presence, it demands attention, demands we expand our understanding, demands we grapple with possibilities that seemed abstract until they became concrete. By late December 2025, we'll know more. By early 2026, analysis will mature, consensus may emerge. The signals will either resolve into natural phenomena or they'll resist natural explanation persistently enough that alternatives become unavoidable. Right now, November 2025, we're in that suspended moment between discovery and understanding, between question and answer, living through history without knowing yet how history will remember this. The electromagnetic pulses continue, 47.3 seconds apart, broadcasting from an object that came from the stars and will return to the stars, leaving us changed simply by having been here, having been detected, having made us ask, what are you? Where did you come from? And are we finally not alone? The universe is speaking. We're listening. And whatever the answer turns out to be, the fact that we're asking the question rigorously, scientifically, collectively as a species, that's already a kind of answer about who we are and what we're capable of becoming.